Multivariable Calculus Math 150 Lecture 10. This is the bonus lecture doing more on optimization.
So it's pretty much 9.5.
So call it 9.5, but in terms of the day, but it means I have actually a free day in terms of what I wear today, because I don't have to match with any previous lecture. And it would probably not be good for me to wear the same shirt 2 days in a row. So what I want to do is I want to start off with one of my favorite problems just because of how many things from calculus it covers. So you have a fixed sum S, maybe it's 100. You want to write S as A1 plus AN. The AIs are positive integers. And you want to maximize the products A1, A2, ... AN. Now the problem is we don't necessarily know what n is. And so let's see if we can think of a few things. We taught before, we know each AI is at least 2. Because if any of the AIs were 1, it wouldn't contribute to the product. What about in the other direction? Can anybody give me an upper bound for how large the A's could be?
98.
Okay. But would you have 98 as one of the A's? Imagine one of the sums was 98. What could you replace it with? So if one of the terms was 98, it contributes 98 to the product. Could I replace something that would have the same sum as 98 but contribute more to the product? What could I replace that with?
49.
And?
49.
So one is I could do 49 and 49. I just need anything better. I could do 96 plus 2. That's going to generalize a lot easier. I could do 49 and 49. But this is going to give me a much larger product in the same sum. What about 97? Could I ever have anything as a 97?
No.
What could I replace that with?
95 would have 2.
And now you can see why I want to do the plus 2 and not the 49, 49. So, long, boring lecture, we get down to 5. What can I replace 5 with?
3 and 2.
3 and 2. We're making progress. What about 4?
2 and 2.
Does it help to replace 4 with 2 and 2?
It's the same.
It's the same. So we're actually indifferent between having a 4 or having 2 2s. Well, if I'm indifferent, let's do the replacement. Because now we know each AI is at most 2, and each AI is less than or equal to 3. So now we know we only have 2s and 3s. Which would you rather have? Do you think it's better to have more 3s or more 2s?
3s.
Why 3s?
Because they're larger.
They're larger,
And it contributes more to the product.
but you get more 2s. Would you rather have a lot of $1 bills or $2 bills? Well, it depends on the relative numbers of them. How should I compare 3s and 2s? I want to compare the contribution to the product. I want to compare the contribution to the sum. How should I compare 3s and 2s? How many 3s are equivalent to 2s? How many 2s?
2 2s is greater than 1 3.
Well, 2 2s is greater than 1 3. Is there some number of 3s that would give me the same contribution as 2s, either for the sum or the product?
2 3s is 3 2s.
2 3s is 3 2s when you add. Right? What's the product here? 9. And the product here, 8. So whenever I have 3 2s, it's better to replace it with 2 3s. So we basically know we just take as many 3s as we can and then finish it off with 2s. So this analyzes the case completely when we have positive integers. And the key observation at the end, make sure you email me, was that 3 plus 3 is 2 plus 2 plus 2, so it's worth trading. Okay. This is fine if this was a discrete math class. This is not a discrete math class. This is a calculus class. So goodbye, goodbye. And all we need to do is the AIs are now positive. And now we can get 1 is less than equal to AI is less than equal to 4. We can make a similar type of argument that if one of the A's is less than 1, we're going to be in trouble. It's going to decrease the product. If it's greater than 4, we can replace it. I am keeping strictly less than or equal to because I want to have a closed set. We talked about the function, f of x is 1 over x, 0 less than x less than 1. This function does not have a maximum or a minimum. And by looking at something like this, by having a closed set, there's a great result from real analysis that says if you live in a closed space, then you will always have a maximum minimum. So I will send you later the link from George Carlin with his airline routine trigger warning. Some of the language may not be language you would typically use in a conversation with your professor, but it's damn funny, and it's funny, and it really illustrates the point. Don't spend time looking for things that don't exist. Look for things that do exist. And the theorem from real analysis will ensure that there will be a maximum minimum. Now the problem is we don't know what n is. So we can play a game. For each n, we could ask what's the best we could do? What's the easiest n to analyze?
1.
1. So if n equals 1, it's kind of trivial. A1 equals s. Building on our remarkable success, what do we look at next? 2. Have we seen the n equals 2 case before? This is a1 plus a2 equals s, maximize a1 times a2. Where have we seen this?
Area.
Area.
Yeah, this is the Farmer Brown. We get a1 equals a2. And now we can continue. And the question is, what if we look at the general case? So we have a1 plus an equals s. We want to maximize a1, a2, an. Does this look like something we can handle using multivariable calculus? Yeah, our function f of a1 through an is just the product. Our constraint function and I can either have it equals s or minus s equals 0. It doesn't really matter which way I write it. So what do we do now to have a constrained maxima? How do we solve it? Take the gradient. So we want gradient of f is equal lambda gradient of g. And now we have a chance to do algebra. Right? Depending on how you do algebra, you can make your life pleasant or painful. Okay? What's the derivative of f with respect to a1?
Well, we don't know how many.
So a2 times a3 da 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 a.
Yeah. Right? Think of these as your x, y, z. If I take the derivative with respect to a1, it's a2 dot 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 an. What's the derivative with respect to a2?
So a1 a3 da 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 a.
A1, a3 dot 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 an dot 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 dot. And what's the derivative of g with respect to a1? 1. Derivative with respect to a2?
1.
With respect to a3?
1.
Okay. So it's just lambda 1, 1, 1. So we now have to solve this system of equations. We know the sum of the a's is equal to s, and we know a2 dot 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 times an equals lambda, a1, a3 dot 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 an equals lambda, and so on and so on and so on. There's a couple of ways to do the algebra. One thing is we basically see that all of these expressions have to be equal to each other. This has an a2, this has an a1. What can we immediately conclude? Yes?
The a2 equals a1.
Yeah, either a2 equals a1 or something equals 0. Since we know nothing equals 0, we can conclude a1 equals a2. Another way you could attack this problem is this is equal to a1, a2 dot 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 an times the vector 1 over a1, 1 over a2 dot 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 1 over an equals lambda 1, 1, 1. Is notice that everything here is almost the same. If I multiply this by a1 over a1, it's the product over a1. If I multiply this by a2 over a2, it's the product over a2. And then I can pull out this whole product over here, and we see that 1 over a1 is the same as 1 over a2 is the same as 1 over a3. There's lots of ways to get to the place that they all have to be the same. So what we see is that when we want to maximize this, the maximum occurs when they're all the same. Okay? Lots of different ways you can do the algebra. There is another way you could do the algebra. And again, we're going to just assume that there is a maximum. This is a result from real analysis. Imagine max has not all equal. So imagine that there is a maximum and not all the coordinates are the same. If not all the coordinates are the same, at least two have to be different. Which two should we say are different?
First and second.
Yeah, without loss of generality, the W log, the most useful log in discussing. Without loss of generality, let's reorder and let's assume the first does not equal the second. So without loss of generality, A1 does not equal A2. So we have the sum is A1 plus A2 plus A3 plus AN, and we have the product is A1, A2, A3, dot, 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 AN. Just focus on this part. Is there something we could do that would keep the sum the same but increase the product? What could we replace the pair A1, A2 with? This is a really good observation.
A2, A1, if you just, wait, no, if they're not.
Well, if we just switch them, it's not going to...
Then it's not going to do anything.
So, but imagine if you want a specific number that it's 3 and 5. What might you replace both of them with? 4 and 4. Or if I gave you 3 and 9, what would you replace both of them with?
6 and 6.
Right. This is the Farmer-Brown problem. If you have a fixed sum, the largest the fixed sum can be, the largest the product will be, is if they're both the same. So if A1 and A2 aren't the same, replace each one with their average. A1 plus A2 over 2, A1 plus A2 over 2. That keeps the sum the same, but it increases the product. So what I'm really trying to highlight is reduce what you are studying to an easier problem, something you've already solved. We've already done the Farmer-Brown problem. So if any two components weren't equal, this can't be the maximum because I've just shown you that there's something better. The problem is, what if there isn't a maximum? Then we might have something that cycles forever. As a really nice extra credit, prove that this process would converge. That if you keep iterating like this, that eventually all the coordinates will converge to the same value. And that will go to the maximum. No matter how you do it, we have now reached the point where we know that the maximum value occurs for given n when they're all the same. So I want to now just talk about how you would finish the analysis. All right, erase this. So if n pieces, the maximum product is going to be S divided by n, because each piece is the same, and what do we raise this to? So each piece is the same, each piece is S over n. What should we raise this to? To the n power. So that's the maximum product. And now we have to see what value of n is going to make this largest. If I'm using calculus, I need to have a continuous variable. What are the possible values of n? It's discrete. Crap. Can anybody give me a function that's related to this with a continuous variable? study f of x. Give me a function that's closely related to this, that equals this when x is an integer.
F of x equals that function, or you like
Tell me what to write.
the Taylor expansion?
I need to know, I want a function that when x is an integer agrees with this, but is defined for all real numbers.
You just replace n with x.
Yeah, do search and replace. Replace every n with an x, and just say, all right, screw that, I'm going to look at s divided by x to the x. And again, I do not care too much about the answer to this problem, I care more about the thought process. How do we find something to study? I know calculus. You know, this is your third calculus class. You should be able to do something with all that stuff you've learned. But I need a continuous function. I now have a continuous function. And I can actually write this as this is e to the x times the natural log of s divided by x. So when you look at this, I have come up with a natural situation where you have a function that involves the exponential of x times the logarithm of x. This is no longer just a cookbook function. This is something that actually arises in the real world. When I teach probability, the function e to the x actually arises. So how would you figure out where this function is largest and smallest?
You take the derivative.
First derivative test. You stretch it.
No.
Oh. You take the endpoint.
Should not do that with a broken hand. All right, let's try again. How do I
Find the
figure out?
domains, or
I'm sorry?
You find the domains first. You find like where, like.
So
where
we
is
know
it?
1 less than equal to x less than equal to s.
So don't
So we find the critical points and what else?
endpoint.
The endpoints. You always have to talk about checking the endpoints when you're trying to find maxima or minima. Right? And then check endpoints. For this problem, it's going to turn out that the endpoints will clearly not give you the maximum. If you think about it, when x equals s, your product is 1. When x equals 1, your product is s. Well, as long as s is a reasonable number, I'd rather have s halves times s halves. So it's not hard to show that once s is reasonable, like 4, it's not going to be the endpoints.
So then you take the derivative.
So now we have to take the derivative. So this is a chain rule. E to the crap, okay? So we get the exponential function back again, x log s over x. And let's do it slowly. And then we have the derivative of x log s over x. So we have to take the derivative. This function here is just f of x, right? So we get f prime of x is f of x, and I'm going to just do it very slowly here. The log of a quotient is the difference of the logs. This is x log s minus x log x, and take the derivative. So continuing, when I take the derivative of the first piece is just going to be the log of s. The second piece, I get to use the product rule. The derivative of x log x is derivative of x, which is 1 times log of x. And then I have x times the derivative of log of x. What's the derivative of log of x?
1 over x.
1 over x. So I get log x minus x times 1 over x. X times 1 over x is known as 1. So we get f of x log of s minus the log of x minus 1. How could I write 1?
X
Oh.
over x.
I could write 1 as x over x. But when you look at this problem, log of s, log of x, how could I write 1?
E, wait,
Log of e.
Close.
Log of e.
Log of e. Because if I write it like this, I can now combine all the logarithms. And so now, if I combine, we get f prime of x is f of x times the log of s divided by, I think, x times e. And we want to find the critical points. How do you find the critical points? When it equals 0. Can f of x ever be 0? No, f of x is the exponential of something. This is never 0. So critical point, we need the log of s divided by x over e to equal 0. When is the logarithm equal to 0? Okay, give me a few more words.
When s over x of e is equal to 1.
When this is equal to 1. So that implies that s divided by x over e equals 1. Therefore, critical point is x is equal to s divided by e. So that's telling us how many pieces we have. This is the number of pieces. How big is each piece? Is s divided by s over e, right? That's the sum. This is the number of pieces. So how big is each piece?
1 over e.
Nope. Close though.
Oh, for sure not. It's e.
It's just e. Now, here is where things get awesome. 0, 1, 2, 3. E is about 2.7. When we did the integer problem, did we want more 3s or 2s? Look where e is. What is e closer to?
3.
E is closer to 3. There's something really deep going on. And I'll send you a paper on this. It's related to which is the best base to use. For a lot of things, base 2 is best. Have we done the binary search game? No. Okay. Is somebody willing to have us get some information about your birthday? Okay. So don't say it out loud.
Yeah.
There are 365 days in the year. I don't allow people to be born on February 29th in my classes. It just throws things off. Okay, I have a deal with admissions. So if I am really stupid, can you give me an upper bound for how many questions it will take to get his birthday?
Log 2.
No, I'm really stupid.
Oh, 365.
365. Were you born on January 1st?
No.
January 2nd?
No.
January okay. But, given that I'm a Williams math professor, I should probably be able to do better. Were you born on July 1st?
No.
And then if I'm wrong, tell me, is it earlier or later?
Okay. Later.
So now with one question, I eliminate half. Were you born July, August, September? Were you born on August 1st? Oh, sorry, July, sorry. All of July, all of August, all of September. Were you born on October 1st?
Earlier.
So now I know it's between July 1st and October 1st. Each time I ask a question, I cut in half. And it will only take me on the order of log of 365 questions to get to your birthday. I'll stop here, just because this is being recorded. All right? And then we'll ask other questions of Paul throughout the year to slowly figure out what his birthday is, and by the end of the... So over here, there's something deep that's going on. For a lot of things, base 2 is wonderful for binary search and how computers work, but in terms of storing information, base 3 actually has some advantages. And it is related to the fact that e is closer to 3 than it is to 2. Now the problem is the number of pieces we want is s over e. Are we allowed to have a fractional number of pieces? No. So what we have to do is we have to find what is the integer value of n that is the best we can do. We only found the best value of x, where x is a real number. We need the best integer value. And so what I'm going to show you is that in many problems, if you know the best real value, you can actually pass to the best integer value. And this will allow me to review curve sketching and some of the rules we talked about last time. Here is x. Here is f prime. Here is 1. We know the critical point is s over e. And the first derivative is 0 at s over e. If x is larger than s over e, Is the logarithm positive or negative? So we have s divided by x over e. If x is greater than s over e, is my thing in the parentheses, is it more than 1 or less than 1?
If s is greater than x over e,
Yeah.
then it's greater than 1.
It's less than
Oh, because
If you want, I'll put the e upstairs.
You're right.
So is it less than 1? What's the logarithm of a number that's less than 1? Positive, negative, or 0? Negative. The log of 1 is 0. If you're less than 1, your logarithm is negative. If you're greater than 1, your logarithm is positive. This is why I love this problem. It gives me an opportunity to review a lot of the stuff you should have seen. So I know the first derivative is negative beyond s over e. What about before s over e? If x is less than s over e, is this parentheses positive or negative?
Well, it's greater than 1.
It's greater than 1. Sorry, this is greater than, thank you. Thank you for answering the question I meant to ask. It's greater than 1, so what's true about its logarithm? So look at this. We know the first derivative is positive. It's 0 at s over e, and then it becomes negative. So the function is increasing up to s over e and then decreasing. So I know it looks something like this. So if I want to find the integer max, what are the only candidates for the integer max? Well, but s over e is almost surely going to be a real number. But look at the function. The function goes up and goes down. So here are where the different integers are. Let's say these are the marks with
The one right before.
yeah, it's either the one right before or
after.
we only have 2 points to check. You know, you just have to check the one right before and the one right after. One of those is going to be the largest. So there's a tremendous amount of good material in this problem in terms of optimization. Some of it is we did it with the Lagrange multipliers, so you can do it that way. We also were able to just step back and think and look and say, well, if two of them weren't the same, we actually just had to solve the 2 problem, and we could get the general case from the 2 problem. And then we wanted to deal with, well, what happens as n varies? Which is the best n? Well, the trick was we actually passed to something that was continuous. We will see this again when we get to your sequences in series. How many of you have seen the different limit tests and whatnot? Okay, so one person has seen it. So we will be doing this trick again of when you're trying to analyze something that takes on discrete values, we will replace it with continuous. If you've seen like the integral test, has anybody seen the integral test? No. All right. They have changed what is covered in calculus classes from when I was a student. So when we get to stuff like that later in the semester, we now have some of this material in the bank. Okay, so this was the first problem I wanted to discuss today. The second one is another application of optimization. It's on the question of inequalities about means. And it turns out this is extremely useful. One of the reasons I like it so much is it gives me a chance to talk to you about the right statistics. So, let me think. Later in the semester, we'll be talking about smoots. Anybody know what a smoot is? Okay, so if you know what a smoot is, it's not a good statistic, but there's some funny stories involving it. Yes, so we will be talking about smoots later. All right, not a good statistic. Let's say you want to have the concept of the mean. So I give you 2 numbers, and you want to give me some new number, which is the mean. Okay? Imagine I am giving you the power of the Almighty, and you will get to determine how the universe is. If you could decide what the product rule should be, when you are creating the universe in mathematics, what would you make the derivative of FG be?
The product of their derivatives.
Yeah, you make b f prime g prime. And if you could make the derivative of a quotient, f over g, anything you want, what would you have the derivative of the quotient be? It would be f prime over g prime. Neither of those happen. But I will let you give me a wish list for what you want for the mean. So, does everybody know roughly what a mean should be? I want you to start quantifying that for me. So we'll assume 0 less equal to x less equal to y. I can always order to make y larger. Can somebody give me a property that the mean should have?
Well, it should be greater than x and less than y, but that's.
So we would want x to be less equal to the mean of xy to be less equal to y. Does everyone agree that this should go on our wish list? That if your mean is somehow lower than x and y, well, I got a 90 on the first exam, an 85 on the second for an average of 30, you'd be upset. Or it could go, I guess, the other way. I got a 30 on the first exam, a 40 on the second, and it averaged it to 102.
That's
Can someone give me another property of the mean? And maybe this only applies for certain values of x and y.
Positive.
So we'll actually have that implicitly from here, but that's a good thing too. Can you think of any pair of x, y where you should know what the mean is?
If they're the same.
If they're the same, what should the mean be?
If x equals y, then the mean is equal to x or is equal to y.
So here are some really good properties of the mean. And then I'll just put one here, maybe the mean of AB and the mean of CD, and then take the mean of that. We would need a way to take a mean of 4 objects, but maybe if you take the mean of the means, that should be the mean of everything. So you can start putting in more and more advanced properties. But what I want you to get out of this is to try to decide what statistic is the right one to look at. When agents are helping negotiate contracts for players, they will come up with all these different statistics that they say really matter. And a lot of them I don't think matter. When they're trying to decide who gets into the Hall of Fame, there's a huge dispute between a lot of the number crunching people and some of the just more just watching and loving the game. Anybody know which shortstop is the most overrated defensive shortstop of all time? Derek Jeter. But what about all those great catches he makes? He makes those catches because he's slow. A faster shortstop would get there in enough time so that he wouldn't be diving and crashing into things. But people remember those plays. And so your senses can fool you. And a lot of us strongly argue that you need to extract certain information and view things impartially and passionately. So here are good properties for the mean. Here are 2 different things that work. The arithmetic mean of x and y is the mean that you've used all your life. It's just add them and divide by 2. The geometric mean is you multiply them and you take the square root. And it turns out the arithmetic mean is always greater than or equal to the geometric mean. More generally, if you assume 0 less than or equal to xi, then x1 plus xn over n is always greater than or equal to the nth root of x1, x2, xn. So this looks like a real good, legitimate multivariable calculus problem. Okay? I want to prove this. What do you think might be useful to prove this? What method?
What do you mean, what methods
Well, how should we try to prove this? We've got,
what we've been doing?
yeah, but what's that method called? Yeah. So in some sense, we're trying to maybe maximize something. So this is not looking immediately like something we can use. So let's change things a little bit. Whenever you see a problem, you should always think about scaling or units. So I once got in trouble in a math class where the professor wrote down an integral and he wrote down what the integral was in terms of the parameter a, and I said, yeah, this can't be right. The units don't work. It's the what? And I was so used to physics classes, I had just put units in my mind. I'm sorry, it has the wrong degree of homogeneity in A. Oh, yes, yes, yes. Different subjects have different language. When I look at this, if I multiply all the x's by 2, what happens to the left-hand side?
Goes by 2.
Grows by a factor of 2. What happens to the right-hand side? This increases by 2 to the n, and then I take the nth root. So what happens to the right-hand side? If I multiply every x by 2, what happens to the right-hand side?
Goes by radical 2.
Grows by a factor of, not by radical 2. If I multiply all the x's by 2, this product increases by a factor of 2 to the n. I then take the nth root, that's just 2. If I multiply everything by 3, the left-hand side goes up by a factor of 3. What does the right-hand side go up by?
Also 3.
3. So I have some freedom now. I can either make the sum of the x's equal 1, or I can make the product of the x's equal 1. I get a choice. So can rescale so that either sum or product is 1. Anybody have any thoughts as to which is better? This is why I like section 1 more than section 2.
You want the geometrically, like so yeah, thank you, the product to equal 1, wouldn't you? Because then it's just.
So what that would be is my constraint would be maybe g of x1, xn is x1, x2, xn minus 1 equals 0. Is that the constraint you want? And then the function you would be differentiating would be this? Or would you rather have your constraint be the sum? Or does it not matter? Because you're going to have to do it either way. To some extent, one of them is your f and one of them is your g. I would probably choose the sum to be 1, but I don't think it really matters. Or instead of choosing the sum to be 1, what might you choose the sum to be? So instead of choosing the sum to be 1, what might be a really good thing to have the left-hand side equal? Yeah, have the sum be n,
Because then you could just divide it.
and then this whole thing would be 1. And if this whole thing is 1, what could I do to both sides? I could raise both sides to the nth power. So I think if I choose the sum to be n, it's going to simplify the algebra, and I can just rescale. So without loss of generality, sum is n, and now we're comparing 1 versus product subject to x1 plus xn minus n equals 0. So I have my function g, my constraint, is going to be x1 plus dot 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 plus xn minus n equals 0. The function I want to maximize is going to be their product. Does this look familiar to what we did earlier today? Where we had a product, and when we take the derivative, you get every term but the one you're taking the derivative with respect to. So the gradient of f is lambda gradient of g. What's the gradient of f? I take the derivative with respect to x1 and I get x2 dot 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 xn. Do you agree it's the same as the product over x1? Is everybody comfortable with that? The first piece is just going to be x2, x3 dot 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 xn when I take the derivative of this with respect to x1. Well, let's multiply this by x1 over x1, and now this is just going to be our product. So is everybody comfortable with that? This makes the algebra a lot easier. So I'm going to just I'll get the product for each one, and I'll get 1 over x1 dot 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 1 over xn equals lambda All right, what's the derivative of g with respect to x1? So I take the derivative of g with respect to x1, what do I get? 1. I take the derivative with respect to x2, what do I get? So I just get all 1s. We know none of the x's can be 0, so we immediately see all the x's are the same. Is this a maximum or a minimum? When I'm trying to look at the product, the sum has to equal n. Do you think this is going to be a maximum for the product or a minimum for the product? How small can you make the product? So you want to look at extreme cases. What would be an extreme case here? Can any of the x's be negative? So if one of the x's was 0, what would that do to the product?
Make it 0.
Make it 0. So the smaller the x's are, the smaller the product. If I made xn large like n and made everything else close to 0, then this product would be very close to 0. This product can't get too large.
So it has to be minimum?
This is actually going to be the maximum point. The minimum point is going to be if I take a lot of the x's to be close to 0. I can make this product as small as I want. This critical point has to be the maximum. The maximum value of f, subject to the sum is equal to n, is going to be when all the x's are the same. So this is a max. And the value is 1 as each xi equals 1. Because we just showed all the x's are the same, and now we use our constraint that the sum of the x's minus n equals 0. Well, if they're all the same, you get n times x1 equals n, so x1 equals 1. So again, a lot of good stuff to think about for this problem. The first thing is, what do we want to study? These are not the only two means you can look at. There are other means. Any physics people here? Okay, so have you ever done like the harmonic mean with the reciprocals? You might see this with resistors.
Yeah, I've never done
Is this in parallel? Resistors in parallel?
this. With the 1 over thing?
With the 1 over thing. I always forget if it's in parallel or in series when you take the resistors and you sum the reciprocals.
No, I think it's...
It's one of them.
Yeah.
It's one of them.
I think it's in parallel, not in series.
I think it's in parallel. I think in series you just add.
You add them in series.
Right. So you've seen this before. You might have seen this also in center of mass problems in physics, where the way you combine some of the masses. We will see an application of this in baseball math. So my claim to fame in baseball is I actually found a theoretical justification for one of the statistics that they use on the main page of standings. And because of this, I've now met many people in the sabermetrics community and gotten some of my students to meet these people and get jobs there. And so I will talk about some of this. Unfortunately, there will be, I'm sure, a camera malfunction at some point during that lecture. But yeah, there are certain things that should not be recorded. We talked about what's the right statistic. Here are two different definitions of a mean. And they both, as if you check, they both have the properties you want. They will both be between x and y. When x equals y, they will both return x. Which one is the better concept? If you want to compute your average, if you use the geometric mean, if you have one really good score and one really bad score, let's say you have 100 on one test and a 1 on the other, you then basically get the square root of 100, which is 10. For the other one, if you just take the arithmetic mean, you basically get a 50. Okay, look at extreme cases. The arithmetic mean is much larger typically than the geometric mean. The way to really relate them is to take logarithms. And if you take logarithms, this is then taking the average. It's going to be 1/2 log x plus 1/2 log y. it's going to be the average of the logarithms. It's what scale do you want to look on. But the big thing we were doing here is to try to figure out what statistic is worth studying. And we had a couple of properties we wanted to mean to satisfy. Both of these functions satisfied that property. There are other things you can do. There's a whole slew of things you can study. And then we were led to this beautiful equation. And when you look at this, is this screaming Lagrange multipliers to you? No. For me, yes, but I've been doing these problems longer than you've been alive. Okay? So when you've been doing them that long, you can quickly look at them and say, yes, this is Lagrange multipliers. I need a constraint. One of my favorite quotes, and if I ever become royalty and get a family shield or crest, there will be a giant hammer on it. Does anybody know the hammer quote?
Is it the hammer of the nail, or is that's fun, but
Similar to that is, it doesn't matter if the pitcher hits the stone or the stone hits the pitcher, it's bad news for the pitcher. If all you have is a hammer, pretty soon every problem looks like a nail. If you are really good at something, you will find a way to convert whatever you have to your skill set. If you listen to any presidential debate, I don't care which candidate you support, well I do, but I'm not going to talk about that. If you listen to any debate and they're asked a question, for the first maybe 10 or 20 seconds they might be polite and pretend that they're going to answer the question that they were asked. But by the end, they are answering whatever point they wanted to make, and they're just using that question as a segue to talk about whatever they wanted. If you have a skill set, you have a tendency to try to convert whatever you have to something where you can use that skill set. There's another way to look at this. If you have a hammer, go to the land of the screwdriver. If they could have solved their problems using a screwdriver, they would have. They can't. It's still an open problem. They don't have the right techniques, probably. Smart people have looked at the problem. They haven't solved it. So I've written papers in marketing and economics and computer science and geophysics and statistics, psychology, lots of different marketing, lots of different fields. I can apply the mathematics in many different settings. And in a lot of cases, well, if the techniques from their subject would have worked, they would have solved it. The great Feynman got a reputation for being able to do integrals that nobody else could do. And one of the reasons he did this is, well, he's at Princeton and MIT. The people who are coming to him are not idiots. If they can't do one of these integrals, he's assuming that they've already tried all the standard tricks. And if one of those standard tricks would have worked, they would have solved it and wouldn't have come to him. He knew a trick that most people did not know, differentiating under the integral sign. So the very first thing he would try is he would try differentiating under the integral sign, basically converting it into this almost like a continuous problem, playing games like that, and here's the solution. Oh my God, that's amazing. So over here, I want to convert this to a place where I can use Lagrange multipliers. I know Lagrange multipliers. To use Lagrange multipliers, I need a constraint. Well, let me make one of the two sides 1. And there's a couple of ways to do this. I could make the product 1, I can make the sum 1, or I can make the sum divided by n equal to 1. I love making the sum divided by n equal to 1 because then I can get rid of the nth root. This is similar to when you've done problems in calculus when you want to find, I want to minimize the distance. Nobody ever minimizes the distance. What do you minimize instead of minimizing the distance?
Time.
Nope. It's related to distance. Distance involves nasty square root. So you minimize the distance squared. Right? If I can minimize the distance squared, I've minimized the distance. But the distance squared is just easier to work with. So over here, the hard part is, what should I do? What should I set equal to 1? Well, you got a couple of natural choices. You know, kill a couple of trees, or take your iPad, write a little bit on it, save the screen, move to another screen, and try and see, is it working? If I make the numerator 1, does that help? Then I've got to raise things to the nth power. That might not be the best, but it's probably still going to work out okay. Maybe I make this product 1, and you just try a couple of things, and if it stops working, then you move to something else. And so here, making the sum equal to n led us to a really nice pair of, here's my constraint, here's my function, and you notice, wait a minute, this is the same thing we were looking at earlier. It's almost like this lecture was prepared. Right? And it's the same algebraic trick. When you do something more than once, it's now called a technique. Okay? When I have a product and I differentiate like this, a nice way of writing it is it's the product divided by 1 over x1, the product divided by x2. All right, so this is a good place to stop.